Okay, so yeah, thanks for coming, and thank you, Alicia, for coming to give us this talk today. Alicia works at the University of Cambridge at the moment, doing a PhD, and you're here to talk to us today about some of your work on heterogeneous treatment effect estimation using machine learning, which we're all really interested in, seeing how that applies to our work here. So yeah, I'll let you go forward.
Thank you so much. Can I just confirm that you can now see my screen, just full screen normal?
Yeah.
Yes? Perfect. Cool. Well, thank you so much for having me. Yeah, my name is Alicia. I'm just about to finish my PhD in the Applied Math Department in Cambridge. And I've been working on using machine learning for heterogeneous treatment effect estimation. And today I just wanted to give you a little bit of an overview of what I've learned in the last 4 years on understanding the challenges, opportunities, and solutions in this space. So the goal of my PhD has been to look at estimating the effect of treatments on individuals. Where we want to ask questions like, will a given treatment work for an individual patient? Using data that observational data that we've collected, which contains things like patient characteristics, treatment status, and observed outcomes. So that's the general setting that we're considering. And we're really motivated by settings where you expect some heterogeneity in effects across patient characteristics, say age. So if the individualized effect in this case here is given by the purple line, then there will be some patients like patient B for whom the treatment will work better than the average, while there are also some patients like patient A for whom it will work worse. Ideally, in practice, we'd like to be able to identify both patients to ensure we treat everyone well in practice. In addition, we're also motivated to use more observational evidence, and that's because clinical trials often use very strict inclusion criteria, which include parts of the treatable population, say in this case, the younger and the older individuals, which is also the people for whom the treatment works less well than the average, which means that in this example, the trial average will likely overestimate the actual average treatment effect in the treatable population. So that this is what motivates us to look at both treatment effect heterogeneity and to move away from using only trial data. Today's talk is set up in multiple parts. Initially, I will start by just introducing our problem setup of potential outcomes and heterogeneous treatment effects. And then I will go into the challenges that I faced and ask the question, what makes heterogeneous treatment effect estimation an interesting machine learning problem? And then we will take a deep dive into the main challenge that I focused on, which is learning heterogeneous treatment effects without the label of interest in this case study. And we will focus on model design, model evaluation, and model selection. And then at the end, I will talk for a couple of minutes about going towards more realistic problem settings. But let's start with a general problem setup. And in my work, I live in a potential outcomes world. I think those of you familiar with causal inference will probably be very familiar with the setup. But I consider a world where we have patients that are characterized by some characteristics X. These are pre-treatment characteristics such as age, gender, and anything else that could be interesting as an effect modifier or as an predictor of outcome. And each of our patients is characterized by so-called potential outcomes. The untreated potential outcome is the outcome that they would that they would realize were they not given treatment, and the treated potential outcome is the outcome that they would realize if they were treated. In general, we are then interested in the so-called conditional average treatment effect, which compares the two, which compares the patient status, the patient outcomes with and without treatment. So it's the expected difference between the treated potential outcome and the untreated potential outcome, conditioned here on the patient characteristics X. And this is individualized to the extent that we assume that every patient is characterized by a unique combination of covariates. Now, the fundamental problem of causal inference is that we only ever observe one of the two potential outcomes. So we either have the treated outcome if the person was treated, or the control outcome if they were in control, but never both. which means that the label of interest, so this potential outcomes contrast, is never observed. And that's very, very different from a standard machine learning problem. So then what makes heterogeneous treatment effect estimation a challenging machine learning problem? And this is my favorite question to ask, especially coming from me. So I come from a machine learning background. So I have to convince my readers that this problem is more interesting than just doing standard supervised learning, so standard prediction. So this is my favorite question to ask because it gives us some insight into whether we can just apply standard machine learning methods or whether there are challenges that require some kind of further model development. Maybe the most important difference to standard prediction settings is the need to make untestable identification assumptions. And this need appears because to make causal inference, we need to argue about what happens under intervention on data generating mechanisms, while in standard prediction, we kind of learn to predict under the assumed status quo. So one thing that we need to assume in the treatment effect estimation problem in general is that there are no unmeasured confounders. So that is that there are no unmeasured variables that affect treatment assignments and outcomes. For example, there cannot be an unmeasured reason that the control group is much sicker than the treatment group. So throughout this presentation today, we assume no unmeasured confounders or ignorability, so that all confounders are included in our pre-treatment covariate X. In addition, we also need to assume that the two treatment groups overlap, or that treatment is assigned with some randomness. And this is to ensure that we could, in principle, observe every individual characteristic with each treatment with some probability. And this is also quite different from assumptions usually made in supervised learning. We assume that the population that we observe is also the one that we want to predict on. In the case that we are happy to assume that our effects are identifiable from observational data, let's move to the challenges inherent to actually learning or estimating using this data. A first challenge appears in that covariate distribution differ across treatment groups if there is observed confounding. So if there are some biases in treatment assignment mechanism. Assume, for example, that the control group is much younger on average than the treatment group. And then in this case, the marginal or population distribution of patient characteristics will differ from the distribution in each treatment group, which means that if we use machine learning to learn to forecast outcome within each treatment group separately, this may not lead to the optimal model for the target marginal distribution because there's a covariate shift across the patient characteristics. This is why there's now a very large literature on applying domain adaptation techniques such as importance weighting or adversarial balancing to counterfactual prediction models. But this is actually not the challenge that I have focused on in my work, mainly because there's a very large literature on this problem already. The core machine learning challenge that I'm interested in is the following. And that is learning without ground truth label in the treatment effect estimation setting. To understand why this is challenging, let's consider first how we train and evaluate standard supervised learning methods. Say we have images like this and would like to learn what's in it. And say our algorithm learns to predict that this is a cat. Now, given that we know the ground truth and that we know that this is indeed a cat, we can happily validate this prediction or assign it low loss. Conversely, if our algorithm also outputs this is a cat for the picture of the clearly the dog, we know for a fact that this is wrong, and we can penalize it somehow using loss functions or simply not selecting this model. Now, for individualized treatment effect estimation, we're giving a patient's characteristics and would like to ask the question, what would have been the difference in their outcome had my patient received the treatment that they didn't? Now, you can already tell by my language that this is not really an easy question to answer. And in particular, what we're trying to output is this difference between the two potential outcomes, right? But in practice, we only ever observe one of the two, but never both. So this is very much a hypothetical comparison. So anything that my individualized treatment effect estimator outputs, I don't really know how to validate. And that's really the core challenge that my work has focused on. And today we will talk about what this means for model design, model evaluation, and model selection in this context. So let's start with the maybe most simple question, and that is how to learn heterogeneous treatments effects without labels by designing models. The simplest solution to estimating heterogeneous treatment effects that's been used a lot recently is what I will refer to as the so-called plug-in solution. And that makes use of the fact that by linearity of expectation, the difference between the two potential the expected value of the difference between the two potential outcomes is equal to the difference of the expected value of the two potential outcomes. And this gives rise to a very simple idea for estimating heterogeneous treatment effects, which is learn to forecast outcomes separately and then to set the treatment effect equal to the difference in these two forecasts. And this is sometimes also referred to as the T-learner. And it's called the T-learner because you split the data in two groups. So the T stands for two. And what would you do is you take the data of the treated group, put it to one side, and you take the data of the control group, put it to the other side. And then you simply use any supervised machine learning method of your choice, say a random forest or a neural network, to learn to predict the treated outcomes simply from the treated group. And you can do the same from the control group and learn an independent model where you learn to predict the control outcomes. And then you simply set your treatment effect estimate equal to the difference between these two individualized predictions. This is a very simple approach and therefore quite attractive, I think, but it also has its shortcomings. In particular, consider an example like this, where we have patient characteristics on the x-axis and expected outcomes on the y-axis, and assume that this, for some reason, was the prediction function for the control outcome in terms of the patient characteristic. And this was the prediction function for the treated outcome. Now, what you can see is these two are both highly nonlinear functions. They'd be kind of difficult to estimate, but their difference is actually extremely simple. Their difference is simply a linear function. Now, if we could target the treatment effect directly instead of estimating the two potential outcomes separately, this would be a much simpler problem. And that is when there is much shared structure across the potential outcomes, learning the treatment effects directly can be much easier than learning the potential outcomes separately, because the potential outcomes separately are quite wiggly functions that are somehow difficult to get right. So if you're simply estimating the two separately, then if you're making an error on each of the two surfaces, these errors might accumulate when you take the difference instead of canceling out. So yeah, what we would like to do somehow is to retarget these plugin estimators to actually target the potential outcomes contrast directly. And one way of doing so is called pseudo outcome regression. And this makes use of the fact that even though the potential outcomes contrast is never observed itself, there are pseudo outcomes that rely on some nuisance parameter eta and that have the same expected value. So that is, the expected value of the pseudo outcome conditioned on X is the same as the potential outcome contrast conditioned on X. And there are a couple of such pseudo outcomes that are motivated loosely by different styles of average treatment effect estimators. So the first one is the regression adjusted pseudo outcome that needs only the potential outcome estimate. A second one is a propensity weighted pseudo outcome that needs only a propensity score estimate. And then the third one is a doubly robust pseudo outcome that needs both the potential outcome regressions and the propensity score to estimate this pseudo outcome. And all three of them, if the nuisance parameters are correctly specified, have the same expectation as the potential outcomes contrast. You're just going to have to trust me on that now. Given these pseudo outcomes, something that you can then easily do is the so-called meta-learner approach, which proceeds in two stages. So in the first stage, we use a machine learning algorithm of your choice to estimate the nuisance parameters. So that could usually be the potential outcomes regressions and or the propensity score. And then in a second step, you plug in the estimate of the pseudo outcome the estimates of the nuisance parameters into the pseudo outcome, and then regress the pseudo outcome on X using your favorite machine learning method. And this can indeed do better than the plugin. And this is because the convergence in mean squared error of the plugin approaches is dominated by the convergence rate associated with the more difficult of the potential outcomes, so the less smooth or the less sparse of the potential outcomes. While the pseudo outcome regression is determined by the convergence rate associated with the Kate itself, and a remainder that's determined by the nuisance components. So if this remainder rate decays fast enough, then if the remainder rate decays fast enough and the Kate is much simpler than the potential outcomes, this translates into the fact that pseudo outcome regressions can converge a lot faster than the plugin approaches. And yeah, so not all the pseudo outcomes have remainders that decay fast enough, but usually it's assumed that the doubly robust pseudo outcome based on the augmented inverse propensity weighted transformation can converge much faster than the plugin itself. Now, the first approach that we looked at here was very much motivated by ideas from statistics. But the second approach to retargeting plugin estimators, it's more core to what we would do in machine learning. So the statistics approach relied on a two-stage procedure, and that's kind of weird for machine learning because in machine learning, we like to do things end-to-end, so in a single optimization step. And therefore, another thing we did is looking at improving the inductive biases of plugin learners. Just as a quick aside, when we talk about inductive biases in machine learning, what we mean is the mechanism by which some functions are preferred over others during learning. And this is usually necessary because problems are underspecified or overparameterized. And this is usually achieved through addition of a regularization term, encouraging some kind of smoothness or sparsity in the learned function. And conceptually, it means that if we have a space of all learnable functions, and let's say the lighter the color here, the more in line with our inductive bias a function is, then if we could estimate, then if this function and this function both get the same error, then we would prefer the function that falls into the middle of the circle. So it's basically kind of the same role as a prior place in Bayesian learning. So in a generic plugin loss function where we're estimating the potential outcomes simply by having some kind of a factual prediction loss, where we just learn to predict outcomes using inputs for each treatment group separately, we will usually also have some kind of regularization term that captures the inductive biases, which means that the weights of the hypotheses functions are separately regularized for each potential outcome because the two learning problems are solved separately. And this, in some way, encodes the inductive bias that each potential outcome is simple unless there's evidence indicating otherwise. But this can go pretty wrong. And to see this, let's consider this very stylized example here of no treatment effect at all. That is, the black line is the potential outcome for both the treated and the control individuals. And that they are distributed like this simply by chance. The observations are the dots that we have. Now, if we were to split the data into the two groups, the control potential outcome that we estimate might look something like this. So this light blue dotted line here, while the potential outcome function that we're estimating using the treated units might look something like this. So despite the fact that they are generated from exactly the same outcome function just by chance, we might get into a position where we're kind of over smoothing on this on both potential outcomes, which will lead to the fact that our Kate estimate, when we just take the difference between the two potential outcomes as here, will look something like that. So all of a sudden, while our treatment effect is actually 0 and constant, because we've regularized the potential outcome function separately, we're getting this completely wrong estimate of the treatment effect. And this is because the inductive bias in a generic plugin estimator is simply not well targeted at Kate, because it kind of encodes this assumption that each potential outcome is simple, but that's not really in line with what we would what the kind of scientific null hypothesis is in this case, which is that the treatment effect is simple unless there's evidence indicating otherwise. So what we did in the follow-up paper on the previous one is to investigate multiple approaches modifying the inductive biases in end-to-end learners to encourage the use of shared or prognostic structure between the potential outcomes and to control the complexity of the learned case explicitly, and in particular to encode this inductive bias that unless there is evidence in the data for treatment effect heterogeneity, the default should always be that there is none. One thing that we looked at is to alter the regularization scheme to target the treatment effect directly. So to apply the regularization term not to the potential outcome separately, but to just simply to their difference. We looked also at reparameterizing the potential outcome functions in terms of the treatment effect. So to fit the treatment effect as an offset to the untreated potential outcome instead of having a treated potential outcome and an untreated potential outcome separately. And the final thing we looked at is to use flexible multitask architectures that learn what to share in a data-driven way. I'm not going to go into the architectural details here, but it basically allowed shared structure across the potential outcomes that's not necessarily additive. Now, with all these different methods, the big question is, how do we evaluate them? How do I test whether one method is better than another? Now, usually model evaluation in machine learning kind of proceeds through benchmarking and very heavily through the use of standardized benchmark data sets. You may have heard of data sets like MNIST and CIFAR and ImageNet that have collected a number of real images for different image classification tasks that have kind of driven the progress of machine learning in image recognition. However, in treatment effect estimation, it's a little bit more tricky because we still have the fundamental problem of causal inference. So we only have one of the two potential outcomes for each individual in any kind of real data. So if we want to evaluate treatment effects directly, we again have to somehow rely on simulations. Something that we found is that the machine learning literature on treatment effect estimation had indeed been relying on semi-simulated data sets, but in a slightly problematic way. And that's because obviously, if you partially simulate your synthetic benchmark data sets, these may inherently and systematically favor some treatment effect algorithms through the choice of data generating process implemented in this benchmark. And this is kind of different from usual machine learning benchmarks, which at least represent data generating processes with real world grounding. So these are usually real images and not simulated images. And in a paper, we showed that this is very much the case for the most popular machine learning benchmarks, the so-called IHTP simulation, that the data generating process inherently favors neural networks over tree-based methods and plug-in strategies over targeted approaches, but is in no way grounded in reality. So that the way that model evaluation had been done in the machine learning literature was extremely biased, probably by accident, towards neural networks and methods that do not target the treatment effect directly. But there was no real reason that these methods should be favored. Of course, there are no perfect alternatives for benchmarking treatment effect estimators in this context, but acknowledging limitations and careful interpretation of results is therefore key. And to see this, I will now show you one of the simulations that I conducted in the papers on actually evaluating these different strategies for estimating treatment effects. So here, the different panels are data sets of different sizes, and on the x-axis, I have increased Kate complexity on each of these plots. So when rho here is 0, this means that there is no treatment effect at all. And as rho increases, the proportion of non-zero terms in the Kate specification kind of increases. And what we did is we compared vanilla plugin learners, so learners that do not target the treatment effect directly, to all these other different strategies. And what you can see as the other different strategies being kind of a pseudo outcome regression that's in purple, and regularization, reparameterization, and flexibility, a flexible specification in the other colors. And what you can see across all panels is that when treatment effect heterogeneity is very low, these more targeted approaches work extremely well and improve a lot over the vanilla plugin learner. And that's kind of expected from the discussion earlier. When the treatment effect is easier to estimate than the potential outcome separately, then it's a good idea to target it directly. However, in the case that we have a lot of data and the treatment effect is also quite complex, we see that this difference in performance kind of diminishes. So it's extremely important to evaluate how these models perform across different scenarios, because if I could have chosen to present only the left-hand side or the right-hand side of this plot, and then would have come to a completely different conclusion about which treatment effect estimator works better than others. Now, we've done a lot of model evaluation on synthetic data, but obviously in practice, we would want to know for my data set, what of the machine learning methods, which one works best. So the final thing that we're going to look at today is a model selection problem. And in particular, we're going to look at the so-called model selection dilemma in heterogeneous treatment effect estimation. So we would simply like to answer the question, if I have my entire Kate estimator toolbox that has many different plugin estimators implemented using different machine learning methods, different strategies, different pseudo outcomes, and I have K candidate estimators outputted, kind of learned on my training data, and I'd like to know which one is the one that I should actually be using in practice. So I would like to know which one minimizes the root mean squared error in this case, but obviously we do not know the true treatment effect in practice. So if this was a normal supervised machine learning task, we would simply use held out targets to evaluate our model. So in my dream world, I would have validation data that I held out from the training data for which I have the potential outcomes contrast, and then simply compare my treatment effect estimator to this held out contrast. Again, just like in the other two parts of this presentation, because of the fundamental problem of causal inference, I again, of course, do not have this contrast available. So this standard validation model selection strategy is not possible to execute in practice. So what we looked at is our different classes of model selection criteria, which all proceed in the same way. So we have training data, and we've trained multiple treatment effect estimators on this training data, and we have K of them. There are different ways of coming up with selection criteria, and what we were interested in this paper was to understand when and why different model selection criteria are a good idea. The first thing that we can do is to use the validation data and to simply keep the factual outcomes, and then to compare the separate potential outcomes predictions on how well do they do in predicting the held out outcomes. So this only works for plugin strategies that also output an estimate of the potential outcome itself, and doesn't work for pseudo outcome strategies that do not output potential outcomes predictions separately. Another thing that we can do is a so-called plugin approach, where we reuse our Kate estimator toolbox and pick our favorite Kate estimator to get a plugin estimate of the Kate on the validation data, and then compare the estimated Kate from the training data to this estimated Kate from the validation data from this plugin estimator. And then a final approach that's been considered in the literature is to use to use the validation data to come up with auxiliary machine learning nuisance estimates, which is again the potential outcomes and the propensity score, and then to construct the same pseudo outcomes that we've already seen for estimating the treatment effects themselves, but now use the pseudo outcome as a target to compare the K estimate against. So basically, there's really three types of strategies that have been considered in the literature. It's comparing treatment effect estimates, comparing potential outcome estimates to the factual outcomes in validation data, and then simply using the t-learner based on best factual predictions. One is simply estimating another Kate on the validation data and using that as a plugin estimate to compare the treatment effect estimator against. And the final one is to construct the pseudo outcome and then compare the Kate estimate against that. Now, intuitively, some of these strategies sound more sensical than others. So what we were interested in is investigating a systematic variation across selectors, where we constructed a lot of simulation studies to investigate how these how these selectors perform in selecting between different estimators in practice. The first question that we were very interested in is whether surrogate selectors are biased towards some estimators. So whether there's some kind of congeniality bias where if you're estimating the plugin estimate in the validation data, whether, let's say you're estimating that using a tree, will it then automatically always prefer to select validation training estimates that also use the tree? So basically, what we tested is whether selectors that are based on either surrogate outcomes, so surrogate pseudo outcomes, or plugin surrogates, whether they prefer their own meta-learner strategy. So what we found is if you're doing the plugin strategy where you're estimating, where you're basically estimating in the validation data another treatment effect estimate, and then use that to select among the treatment effect estimates that you already have from the training data, this very much favors estimators that use the same meta-learner strategies. While if you're using the pseudo outcomes, this doesn't seem to have such a bias. And similarly, we were interested in the question whether selectors that are implemented using a specific machine learning method prefer their own machine learning method. And again, we found a similar thing, that the plugin estimators, every plugin estimator implemented using a linear regression, for example, very much favored selecting linear regression methods that actually also use linear regression, whereas the pseudo outcome selectors did not display such a bias. A second question we were interested in was whether, what we found is that factual selection, so using factuals alone to select models that predict very well, we found that didn't work very well in practice. There was always a pseudo outcome or plugin selector that worked better than using factuals only. And we were interested in why that happens. So in particular, we were interested in why do we lose out using factual evaluation? Is it because they can't evaluate all types of estimators? So as I said earlier, you can only evaluate something using a factual selector that also outputs a potential outcome estimate. But not all methods output a potential outcome estimate. So immediately the factual selector can only select among those that estimate a potential outcome separately. Or there might be something else. This is because they're not really well targeted at the thing that we're interested in. So what we did is we leveled the playing field and give every selector the same estimator, but found that even given the same estimators, factual selectors do not necessarily pick the best Kate estimator. And this is because they have wrong priorities. They choose estimators that do better at potential outcome prediction, but not every estimator that does better at potential outcome prediction also does better at estimating the Kate. And this is because, say you have two estimators that both, you have one estimator that does very well at estimating the Kate, has a very well at estimating the potential outcomes, but has a very small error. But on each potential outcome surface, the errors go in opposite directions, kind of one underestimates, one overestimates. Whereas you can have another potential outcome predictor that does quite badly at, that makes a much larger error at estimating each of the potential outcomes. But because you take the difference between the potential outcomes, and this estimator happens to make the same large error in the same direction across both potential outcome surfaces, this error can actually cancel out. But a factual selector very much cannot capture that because it doesn't consider the Kate estimate that comes out of it. So these were two small questions that we looked at in our paper, but our paper has a kind of a plethora of experimental studies on the shortcomings of different selection metrics. And we basically found there's no magic bullet. There's none that always works really well. But to check those out, have a look at the paper because there's just a little bit too many empirical studies that we conducted there to talk about them now all. Because I wanted to take the last couple of minutes, I've been just looking at time, last couple of minutes to talk about going towards more realistic problem settings. So the machine learning Kate estimation literature has focused on a very, very small subset of real problem settings. And it's predominantly been focused on the problem setting that I've discussed here, which is the static binary Kate estimation problem, basically. So if this was the landscape of heterogeneous treatment effect estimation problems that exist in practice, we've really only, in machine learning, really only covered this one setting, which is static outcomes, binary treatment, kind of that's it, standard outcome. But obviously, and I guess I don't have to tell you that, real data is a lot more sparse and a lot more biased. There's a lot more problems with it. And what we've tried to start to do over the last couple of years is to look at other problem settings that appear kind of in this Kate estimation landscape. We've considered multiple or more complex treatment strategies, missing inputs or outcomes, censored survival outcomes, competing risks, and informative sampling, and obviously there's a lot more. But how these have been treated in the literature so far is kind of very, very disjoint. So for every one of these treatment, kind of these new settings, we consider them separately. And usually what happens is each of these just induces a new source of missingness. And with that new source of missingness comes a new source of covariate shift. So let's say censoring, random missingness, but not completely random missingness, informative sampling, they all shift the population that we're observing. And a lot of the solutions ultimately just handle it by introducing a new importance weighting term to correct for the shift separately. But something that would be very interesting and that we haven't looked at all yet is how we could best address multiple sources of missingness in covariate shift jointly, because a lot of these problems usually happen together. But yeah, this is something we haven't actually done yet, but would be very interesting, I think, in the future to kind of go towards more applicable Kate estimation methods that can actually handle a lot of these sources of covariate shift jointly. So to conclude this very quick overview of what we've done in the Kate estimation, machine learning for Kate estimation space, is that my main takeaway is that Kate estimation very much is an interesting and challenging machine learning problem. So I think there are two parts to the problem. One is from an application side, you would like to use machine learning for the problem, but I think it's also from a machine learning perspective, it's a very interesting problem to study because it has characteristics that normal supervised learning problems don't have. So it makes it very interesting from a methodological perspective. However, I think my own main takeaway is that difficulties in evaluation and model selection remain really challenges for deployment of these methods in practice. And domain expertise is very much crucial in constructing better data sets and choosing good inductive biases. Because so far, most of the data sets that we have to compare these methods somehow are simulated in unrealistic ways and do not necessarily reflect characteristics that we will have in practice. So given the fact that we rely so heavily on benchmarking these estimators on simulated data sets, it would be great to have input from real domain experts in how we best construct benchmarks in the setting, and also to choose good inductive biases for the estimators that we encode in them. And then finally, obviously, as I said at the end, in reality, static Kate estimation is only a small subset of a much broader class of problems with sparsely observed outcomes that we encounter in practice, especially in health application. So I think it would be extremely interesting to investigate whether we can do better than solving each missingness challenge separately. This work and my entire PhD was supported by AstraZeneca and obviously by my supervisor, Mehala van der Schaar. And yeah, if you're interested in any of the work, the presentation here is based on the following papers and references therein. And there's also a lot of code available to replicate all the experiments in the papers and what I've presented here today, using neural networks and random forests and anything else you would like to use. So thank you so much for listening, and very happy to answer any questions if you may have them.